What's up? Welcome back to my tutorial channel. Daniel's here, and today I'm gonna continue on topic 6, the normal distribution, and I'm gonna talk about part 3, the central limit theorem for proportions. In this part 3, I'm gonna first show you how to construct a similar distribution for a simple proportion. Then I'm gonna walk you through the central limit theorem for proportion and how to apply the central limit theorem for proportion in practice. First, sampling distribution of a simple proportion. So what is a simple proportion? To understand what a simple proportion is, let's walk through this example. A computer retailer wants to estimate the proportion of people in her city who own laptop computers. She cannot survey everyone in the city, so she draws a sample of 100 people and surveys them. It turns out that 35 out of the 100 people in the sample own laptops. So we have a sample of 100 people, and 35 of them have one common characteristics. So the proportion 35 over 100 is called the simple proportion and is denoted by p hat. And the proportion of people in the entire population who own laptops is called the population proportion and is denoted by p. Here p is unknown. We don't know about the population. We should take a sample and we know the sample proportion, but we don't know the population proportion yet. So definition: in a population, the proportion who have a certain characteristics is called the population proportion and denoted by p. In a simple random sample of n individuals, let x be the number in the sample who have the characteristic. The sample proportion is p hat is equal to x over n. So that is the difference between sample proportion and population proportion. Now we learn how to construct the sampling distribution of a sample proportion. Let's consider tossing a fair coin 5 times. This produces a sample of size n is equal to 5, where each item in the sample is either a head or a tail. The proportion of times the coin lands heads will be the sample proportion p. Because the coin is fair, the probability that it lands head each time is 0.5. Therefore, the population proportion of heads is p is 0.5. So p is 0.5. Here is the population proportion. That means it's the theoretical value. Now, when we look at the outcomes, there should be 32 possible samples of size 5, and their sample proportion of head are presented in this table. So a sample of size 5 can be either tail, 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 or tail, 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 head, and so on. For each of these samples, we compute the proportion of landing head. For example, when you look at the first sample, tail, 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 we have 5 items and none of them is head. So the proportion of getting head is 0. Similar for the second sample, tail, 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 head, we have 1 head out of 5 tosses. So the proportion of landing head is 1 out of 5, which is 0.2, and so on for the rest. So now after we compute the sample proportion for the 32 possible samples, we have got a new sample of some value, 0.0 0.2, 0.2, 0.4, 0.2, 0.4, 0.4, 0.6, 0.2, 0.4, 0.4, 0.6, 0.4, 0.6, 0.6, 0.8, 0.2, 0.4, 0.4, 0.6, 0.4, 0.6, 0.6, 0.8, 0.4, 0.6, 0.6, 0.8, 0.6, 0.8, 0.8, and 1. So here you see that if several samples are drawn from a population, they are likely to have different values for p hat, because the value of p hat varies each time of sample is drawn. P hat is a random variable. You see that these numbers are the value of the random variable p hat. And definitely p hat should have a distribution, a probability distribution. So we are going to investigate the probability distribution of this random variable p hat. So we are going to compute the variance, the mean, the standard deviation of p hat, and consider how the density curve look like. So now we are going to make a summary of the sample distribution of the sample proportion and compare with the theoretical population values. For the population value, here we have one parameter. The population proportion P is 0.5 because the cone is fair, so the probability of landing head is the same as the probability of landing tail. And for the sample distribution summary, the mean of the sample proportion is 0.5. The variance of the sample proportion is 0.05, and the standard deviation is the square root of the variance, so it's 0.2236. Here, there is a relation between sigma and p and the sample size. Sigma is approximately square root of 0.5 times 1 minus 0.5 over 5 in the square root. So in this section, we are going to admit that the mean of the sample proportion is about the population proportion, and the standard deviation of the sample proportion is square root of the population proportion times 1 subtract population proportion over n in the square root. Summary. Let p hat be the sample proportion of a single random sample of cyan drawn from a population with population proportion p. The mean and the standard deviation of the sample distribution of p hat is mu of p hat is p, and sigma of p hat is square root of p times 1 subtract p, the whole thing divided by n in the square root. Let's do one more example. The soft drink cups at a certain fast food restaurant have tickets attached to them. Customers peel off the tickets to see whether they win a prize. The proportion of tickets that are winners is P is 0.25. That means suppose they have 100 tickets, 25 of them give the customer a prize. A total of 70 people purchase soft drinks between noon and 1 p.m. On a certain day. So we are going to find the sample distribution of the sample proportion. Here the population proportion is known as 0.25, and we are going to investigate the sample distribution of the sample proportion. That means the proportion of 70 people who win the tickets. So by the sample distribution, the mean and the standard deviation of the proportion p hat of 70 people sampled that win a prize is mu of p hat is p, exactly p, which is 0.25, and the standard deviation sigma of p hat is square root of 0.25 times 1 subtract 0.25 divided by 17 is square root and is equal to 0.0518. So now we go to the most important thing in this topic, the central limit theorem for the proportion. Last video we learned about central limit theorem for the mean, and now we learn the central limit theorem for the proportion. Basically, we're going to construct the histogram and the density curve for the sample proportion when the sample size increases, and observe how the shape of the histogram and the shape of the density curve change when the sample size increases. First, when here again we consider tossing a fake coin. First, when we have the number of tosses is 5, the histogram is symmetric and quite normal. The density curve is quite normal, centered at 0.5, at p 0.5. When the sample size increases up to 50, the histogram and density curve is even closer to normal. However, here we choose the p is 0.5. So even when the sample size is 5, the histogram is still symmetric because 0.5 is equal to 1 minus 0.5. So suppose we choose a different value of p, let's say 0.1 or 0.4. The first histogram should be skewed, not symmetric. However, if we increases the number of sample size, increases the sample size, it's still approximately normal. So here we have a remark. When p is close to 0 or close to 1, a larger sample size needed before the distribution of p hat is close to normal. So the central limit theorem for proportions say that let p hat be the sample proportion of a sample size of n and population proportion p if n times p is at least 10 and n times 1 minus p is at least 10. Then the distribution of p hat is approximately normal with mean and standard deviation. Mean of p hat is p and sigma of p hat is square root of p times 1 subtract p over n. And the procedure for computing probabilities with the central limit theorem is the first step we have to check to see if the central limit theorem is applicable. That means we have to check the condition n times p is at least 10 and n times 1 minus p is at least 10. If both of them are met, then the central limit theorem is applicable. Otherwise, we cannot apply the central limit theorem. Step 2. Once the central limit theorem conditions are met, we go ahead and compute the mean and the standard deviation of the sample proportion, mu of p hat and sigma of p hat. And then step 3, we get the normal curve and shape in the area to be found. And step 4, find the error using table A2 or technology. So let's do one example. According to a recent Harris poll, chocolate is the favorite ice cream flavor for 27% of Americans. If a sample of 100 Americans is taken, what is the probability that the sample proportion of those who prefer chocolate is greater than 0.30? Solution. So the first step, of course, we are going to verify the condition of the central limit theorem. N here is 100, p is 0.27, so n times p is 27 is greater than 10. Then the second condition, n is 100, 1 minus p is 0.73, so n times 1 minus p is 73, which is at least 10. We may use the normal curve. Step 2. Now we see that the central limit theorem is applicable, so we need to compute the mean and the variance of the similar distribution. The mean is exactly the population proportion, 0.27, and the standard deviation is square root of 0.27 times 1 subtract 0.27 over 100, which is 0.044396. Step 3. The probability that the sample proportion of those who refer chocolate is greater than 0.30. So here we want to compute probability that P is greater than 0.30, and we are going to use standardization. So we subtract both sides by the mean and divide both sides by the standard deviation. The left hand side becomes Z, because this is part of the central limit theorem. The central limit theorem say that when the two conditions of central limit theorem are met, the same proportion follow normal distribution with a mean mu of p hat and sigma of p hat. Use standard deviation when p hat subtract its mean and then divide by its standard deviation, we have the standard normal distribution. So here the problem turns out to be for probability that Z is at least 0.68, which is finding the area to the right of the Z-score 0.68. So to use the table A2, we have to use complement rule. So this is equal to 1 subtract probability that Z is less than 0.68, and we use the table A2 to find the area to the left of 0.68, then subtract from 1 to get the area to the right of 0.68. And this is how the curve look like. We find the area to the right of 0.3, and the Z-score 0.3 is 0.68. So that's it. That's all for today. Thank you so much for watching my video. I hope you guys find my video helpful. See you next time. Bye.